we move along to 4.7, you notice we skip sections 4.5 and 4.6. Hey, if you want to study those on your own, you're certainly welcome to. You bought the book or rented the book at least. But for the purposes of our course and our schedule and all that, we're just going to go right along to optimization. Okay, optimization, it's going to have a similar feel to related rates. These are not short problems. They take a lot of time, but this is a massive, massive usefulness of derivatives. I would say for probably a lot of you guys and where you're going to go, optimization is going to be the most useful thing that you might get out of this entire course. Think of optimizing like we want to optimize our profit or minimize our costs or optimize the amount of resources that we have to get something done. How can we use calculus to help us out there? Okay, so before we get into the big examples, this is all going to come back to finding absolute maxes and mins on the interval a to b. So we're going to do a quick example here. We did this back in 4.1, which perhaps in our summer course, it wasn't very long ago at all. But I typically review this because it's typically been a couple of weeks. Okay, so a quick example of finding an absolute max and min. How about f of x equals x squared plus 3x minus 5 from negative 4 to 2? How do you find that absolute max and min? Well, you start by finding the criticals. So that means we need a derivative. And we're going to take a look. Hey, when does that derivative equal 0? Are there any times where it does not exist? Okay, so I'll just show you my work here. Pretty quick to solve this derivative equal to 0. And, well, what f prime of x equals 2x plus 3, there's no time where it does not exist, especially not in our interval. What do you do once we just have the one critical number there? What do you do then? You take that critical and you plug it back into the original function. So we get this fraction. I invite you to check my work. I got f of negative 3 over 2 to equal negative 29 over 4. Right? What else do we do? This is like step 1, all of that. Then step 2 says check the y values of the endpoints. Plug these both into the original. So I'm going to do that here. At negative 4, I got negative 1. And f of 2, I got 5. Okay. So what does that mean? Well, we've got this list of the important y values. The biggest one is the absolute max. The smallest is the absolute min. And so we got our answers right there. The biggest y value here was 5. The smallest is the negative 29 over 4. There you go. Okay. Keep this process in mind as we look at this example now. Like I said, optimization got a very similar feel to related rates, so the questions are going to be, the sentences or maybe a paragraph. And the most difficult part is just coming up with the equations in the first place, right? So if you think about finding an absolute max and min, you're given a function and you're given an interval. And so we're going to have to come up with a function and an interval. And once we have those, then we can go through the process of finding the absolute max or the absolute min, whichever one the question is asking for. Okay, let's read this together. A box with no lid has a square base and a surface area of 48 inches squared. What dimensions produce a box with maximum volume? Okay, so imagine, you're at a factory or you're designing this thing and you say, okay, I have a limited amount of material to use. I only have 48 square inches and I want to make the biggest box that I can. But a couple of things, it's got to have a square base, and there's no lid on it. There's no top. But I know how much material I have. How big a box can I make? Okay, the first thing we want to do is a drawing, because that's going to help us get our equations. So I've got my drawing here of my box. Very nice, right? It's a rectangular box, right? And now let's start to label this thing with some variables. So we know the base is square. So I'm going to say x and x for my square base. It doesn't say anything about the height. So that's just going to be some other variable. Maybe we just call it y. So our box is x by y. Okay, well, that's my drawing, and I've labeled it. That's all I got to go on, square base. And I'll keep in mind there's no lid on the top. Where do we go next? Okay, notice the question talks about two different quantities. We need to maximize the volume, and it also mentions surface area. Okay, so let's think about both of those. When it comes to this drawing, what's the volume of this box? Say, well, volume is length times width times height. So the volume is x by y, or x squared y. Okay. So I'll pull this down, it'll be there in a second. It also talks about surface area. What's the surface area of this box? And now it's important that there's no top on it. You think, well, there's 5 sides, right? The base, the front, the back, the left, the right. And if you add all those up, you get the surface area. So the base is x squared. And each side, since it's a square at the bottom, each side is x times y. X times y, this front part is x by y. The the left side is x by y, and the back is x by y. So there are 4 sides that are x times y, and the base is x squared. So that's what I've got down here. My volume and my surface area. Now notice my volume, I just say V equals x squared y. But the surface area, they tell me in the problem what that's supposed to be. So my 5 sides, x squared plus 4xy, I know that's going to equal 48. I'm going to use all 48 square inches of material to get the biggest volume. So just getting these equations, again, that can be of the most difficult part, or at least it can be, the most. Here it's not so much difficult in terms of, well, we had to go through all these steps, but we had to recognize that we needed these things. So again, every problem that's going to mention 2 quantities. One is what you're trying here to maximize, and then the other one is just some other quantity that they're going to tell you the amount. Okay. Here's what we're going to call them, just to reference these things. So the volume with just the V, right? V equals, that's what we're trying to optimize. Now we're trying to maximize it in this example. In a different example, we might try to minimize something, but that's what we optimize. The one where you know what it's equal to, we call that the constraint. We have a limited amount of material. We're constrained by this. Hey, if we wanted to make a bigger volume, we'd just increase the surface area. We could do whatever we wanted, but we're limited, right? We know how much we had to work with. Okay, I think I've said enough. Here's what we're going to do. This, at the end of the day, this is an absolute, finding the absolute max or min problem. Here it's finding the absolute max. Trying to find the absolute max of the volume. So we need one function and an interval, right? And then we'll go through the steps. But how do we do that? And even at this point, we've got these 2 things. This is the function. What we're trying to optimize is the function in the absolute max or min problem. But we're hindered in that right now because we've got volume in terms of 2 variables. So well, how do we do, we can't do anything with this yet because we've got x's and y's. We need the volume in terms of one variable only, and that's what I've got right here. We need v equals x squared y in terms of one variable. If we can find a way to write this in terms of only one variable, then we can take derivatives, then we can go for it. Okay. The way this one is set up, it's going to be easier to get this in terms of x. How are we going to do that? We're going to use the constraint. So you always leverage the constraint to get what you're trying to optimize in terms of the one variable. How? Hey, let's solve for y. Let's subtract x squared. Let's divide by 4x. And we know how x and y are related. We can put this whole thing in for the y. And then we'll have volume in terms of x only. And here I've got it at the bottom. So always use your constraint to write what you're trying to optimize in terms of one variable. Okay. So again, the substitution, boom. Now, so that's big. If we've gotten this far with the problem, we're off to a great start. As it's written, we want to clean this up. We want to simplify that. We know we're going to have to take a derivative of this pretty soon. So let me keep that still on the screen and show you where I went next. Let's try and write this as a polynomial. So I'm going to split this fraction. 48 over 4x is 12 over x. X squared over 4x, think of it as just x over 4. And then distribute the x squared. Let's get rid of that. Distributing the x squared, 12x minus 1/4 x to the third. I like that 1/4 x to the third because that will mean my derivative comes out a little bit smoother. Okay, this is great. We've written the volume in terms of only x, just one variable, and we've really cleaned it up. So we're going to be able to take a derivative very easily. We're not ready yet. There's another piece to the puzzle. We need an interval of x. So you might say we need the domain for x. We need the interval of x, however you say it. How are we going to find an interval of x? Okay. Yeah, great question. We need to consider the entire context of the problem. We're going to consider the constraint. So that might be really helpful in getting the interval of x. And also just even going back to the original drawing. Okay. So here we've got the drawing and we've got the constraint. So if you look between these, let's think about smallest and biggest, right, to get the endpoints of the interval. What is the smallest that x could be? Right, so we'll keep in mind that we're making a box. We also have this constraint. And we can say, you have to kind of bear with me here with the logic. We can say, I'm going to show you the smallest and the largest actually, or the beginnings. The smallest that x can be is 0. Now here's the thing. X cannot actually be 0 because if x is 0, then we violate our constraint, right? And we'd have a surface area of 0. However, x is allowed to get infinitely close to 0 and still just be a little bit positive. Okay, so imagine maybe the picture. Imagine the picture like this base shrinking down to a tiny little square, but we still have a surface area of 48. So what would that mean? If our base shrinks down to a teeny tiny little square, that would just mean it needs to be super, super, super tall in order to still have that surface area of 48, right? It would just get crazy tall. And if there's no definitive point where we should stop, we can keep shrinking it, then we're just going to have to say 0. Now, obviously, it can't actually get to 0, but it can get infinitely close to 0. So we just got to go with 0 itself. Okay? Then the question becomes, if you buy that, then the question becomes, well, all right, if x is 0 is the smallest that x could be, then what is the largest that x could be? And oftentimes, to get the largest x value, you just think of the smallest y value and you work from there. Okay? So again, let's go back to the drawing to make sense of that. If x gets bigger and bigger and bigger, we make that square larger and larger, that means it has to get shorter and shorter to still meet that constraint. So how big could we make this thing, and still keep the 48? Now here we could say that y becomes 0, right? It shrinks down to nothing. That means the volume would be 0, but let's just look here. If y shrinks to 0, what x value would come out of that? And now this we can solve. This makes sense. If y shrinks down to 0 from the constraint equation, then x squared equals 48, and x equals the square root of 48. Now, I know that could be simplified, but I'm just going to leave it like this. So it even kind of gives a good idea. We know where it came from. Now, this one does make sense, and this could happen. It's not a theoretical thing. If we make that square big enough, we're going to take up all the surface area just with the base. So if x is root 48, then the area of our base is the 48 square inches, and we've just got a square with no height to it. Well, clearly that's not going to maximize the volume, but it is the biggest that x could be. So that's the limiting boundary, right, for x. So x we know is somewhere in between 0 and square root 48 for whatever box we're going to make. Okay, great. So we have our function v equals 12x minus 1/4 x to the third. And we have our interval. Now, again, I totally hear you. The 0 is a little sketchy. It cannot actually get to 0, but it can get infinitely close. But this one it certainly can get to. Another thing on the interval, and the interval really gives people a hard time because it's just pretty much conceptual in a lot of cases. The boundaries on the interval, neither one of them are going to maximize the volume. We get it, right? If we make the entire base all of the surface area, that's not going to give us the biggest volume. If we shrink the base down to almost nothing and just make it taller and taller, that's not going to maximize the volume. But we still need this interval to show that the x value we do come up with really does give us an absolute max. And we're going to see it played out in the last few steps here. Okay, now we've got it. Function interval. Let's go for it. We need a derivative. Here, v prime equals 12 minus 3/4x squared. Because we cleaned up our function, our derivative, very quick, we need to set our derivative to 0, and we need to consider when it does not exist. Okay. Well, let's just answer this one. Well, that's none, because, we've got a polynomial again. But what about when we set it to 0? Well, let's see if we subtract the 12. And now maybe we multiply both sides by -4/3, the reciprocal. We'll get x squared equals 16. And square rooting x equals 4. Now you might think, hey, shouldn't this be plus or minus 4? It should be, but remember that our interval of x is only between 0 and root 48. So we can immediately ignore the -4 and just go with x equals 4. Okay, so we only get the one critical value between 0 and root 48. What do we do next? If you remember the steps, we plug our critical number in to the original volume equation function. So we calculate v of 4. There it is, 12x minus 1/4 x to the third, plugging in the 4. And I recommend, once you've made sense of what I'm doing here, go ahead and compute that number with me. V of 4 turns out it's equal to 32. Right? Then we're going to plug in our endpoints of our interval also into V. So when we plug in 0, well, 12 times 0 minus 1/4, 0 to the third, that's going to be 0. How about plugging in root 48? Now this is kind of surprising, so I invite you to do it, but when you plug in root 48, you never would have expected it, but you actually do get 0. And it makes sense if you think about that drawing again and the constraint. The volume would be 0 at both of the endpoints. So what does that tell us? Okay, let's stop here. And I'm going to go back to the original question. What were they asking? What dimensions produce a box with maximum volume? Okay, we're at a critical moment. We just found right there the absolute max, right? 32 is bigger than 0 or 0. And in this case, it represents a volume. This is the maximum volume. The 32 is. However, that's not what they asked for. They didn't ask what's the maximum volume. If they did, we'd be done, 32. They ask what dimensions produce the maximum volume, right? Well, what dimensions, like the x and the y, length, width, and height, what dimensions produced it? Okay, well, it came from x equals 4. X equals 4 gave us that volume of 32. We need the y value as well. Well, we could go back to y minus x squared over 4x, way back from the beginning when we first solved for y. We could plug our 4 into that, and we'll get a 2. So considering the drawing of that box, that it was x by y, we can say the dimensions are 4 inches by 4 inches by 2 inches. And that seems like a very small box now that we come to it. But if we made such a box 4 by 4 by 2, it would have a total surface area of 48 inches squared. Well, that's what, 48 inches squared is like 4 square feet. So like 2 feet by 2 feet. 4 inches by 4 inches by 2 inches. That seems very small. But okay, that's what it is. Maybe I'm off on the way I'm wrapping 48 inches squared. No, 2 feet by 2 feet would be a lot bigger than that. Okay, my mistake. All right. No, this seems right. 4 by 4 by 2, that'll maximize the volume. I should have stopped a couple minutes ago. Let's stop here. More examples to come.